When I publish data about performance, people often point out that CPU caching is likely having an effect on the results. So I thought I'd make a video exploring the effect that the CPU cache can have. If you're watching this in January of 2024, I'm looking for work. If you know of an opening that I might be a good fit for, please see the video description for a link to my LinkedIn. I wanted to dive in and understand just how much of an impact CPU cache misses can have, as well as what developers can do to avoid cache-related performance issues. Let's start by reviewing what the CPU cache is. Simply put, the CPU cache is a small amount of high-speed memory incorporated directly on the CPU. At a high level, the advantage of the cache is that cache access is generally 200 times faster than main memory access. Additionally, only one CPU can access main memory at a time, so CPU caches can often improve multiprocessor performance. Modern computers usually have multiple caches, but we'll keep things simple for this explanation and view them all as a single cache. CPU caches can be different sizes depending on the hardware. To give perspective, my computer has a 512 kilobyte cache. As a result, it's pretty easy for modern software to want to access more data than can fit in the cache. Computers manage data in units called cache lines. A typical cache line is 64 bytes, although it seems as if some hardware may use other sizes. Anytime the CPU needs data that isn't in the cache, the entire cache line in which the data exists is copied from main memory to the cache. This results in a phenomenon called cache locality, whereby data that the program needs may already be in the cache because of data close to it. Remember this concept, it will be important later. When the CPU requires data that isn't in its cache, it has to wait for main memory to copy the data to the cache. This is called a cache miss. Let's see how much this hurts performance. My test program has two tests. Both tests create an 8 gig array of integers. This is big enough to guarantee that it can't all fit in the CPU's cache. The cache-friendly test then iterates through the array in order. This creates a high likelihood that the next iteration will access memory that was pulled into the cache by the previous iteration. The cache-unfriendly test does the same simple math, but accesses the array elements at random, thus creating a high probability of cache misses with each iteration. The performance difference is quite remarkable, far more than I expected. The cache-friendly code is 5 times faster than the unfriendly code. The reason for this is that each time a cache miss occurs during serial access, the cache line includes values that will be needed for the next iteration. Whereas in random access, cache misses are unlikely to include data useful to the next iteration. While this is close to a worst-case scenario, it does demonstrate that, in performance-critical cases, programming to take advantage of cache locality can be worthwhile. So how do we do this? We've already seen the first rule of thumb: access data in a predictable manner. This allows the CPU's cache management circuits to operate in the manner they're optimized for. The second rule of thumb: keep your data as small as possible. It should be obvious that smaller data will result in fitting more in each cache line. Since the size of an int on a 64-bit machine is 8 bytes, I reran the previous experiments with 4-byte and 2-byte ints. You can see the results. It's interesting to note that accessing the data sequentially results in a much larger improvement than just reducing the size. But in the case where sequential access isn't possible for some reason, using the smallest data type possible certainly helps. Another rule of thumb is to group data that's commonly accessed together into structs. Doing so greatly increases the chances that all the data will occur on a single cache line. You can see here the tests I used and the speed that resulted. A final rule of thumb is to prefer values to pointers. The logic behind this is that allocation of data into a pointer could grab memory from anywhere, thus resulting in access being quite fragmented. You can see the speeds achieved by my two tests here. As always, these are just techniques to try. You should always test performance under the most realistic conditions you can create before making determinations on the best way to structure your code. Many other factors can come into play in some use cases that can hurt performance more than cache locality can help it.